The age of Earth was first measured not with fossils, but with the heat of a cooling planet and the ticking of radioactive atoms. In 1650, Archbishop Ussher declared creation began in 4004 BC. By 1862, Lord Kelvin calculated between 20 and 400 million years. Then, in 1907, Bertram Boltwood read a rock and found 2.2 billion. Who was right? And how could a stone hold a clock older than time itself? That question begins with a single man and a single date. In 1650, Archbishop James Ussher of Ireland cross-referenced the genealogies of the Bible, counting the generations from Adam forward, and arrived at a precise answer. Creation, he declared, began on the evening before October 22nd in the year 4004 BC. It was not a guess softened by doubt. It was a verdict, and that verdict did not stay in a scholar's study. Ussher's figure was printed in the margins of English Bibles for centuries, sitting beside the opening lines of Genesis as if it were scripture itself. It first appeared in his 1650 Latin work, the Annals Veteris Testamenti, and by 1701 it had been inserted into the authorized King James Bible, where it lingered in editions well into the 20th century. Ussher, who died in 1656, had pinned the whole of history to 5,656 years, and few dared question the arithmetic of a man buried with honors in Westminster Abbey. Generations grew up reading that the world was roughly 6,000 years old. To doubt it was to doubt God. But while the faithful read that number, other men were reading a different text, one written in stone. Geologists who bent low over cliff faces and riverbanks began to feel that 6,000 years was not merely wrong, it was absurd. The rock told a story that no genealogy could contain. The man who felt this most fiercely was a Scottish farmer and physician named James Hutton. Born in Edinburgh in 1726, he had trained in medicine at Leiden before turning to the soil of his farm in Berwickshire, where the daily grind of plow and rain taught him how slowly land wears away. In 1788, standing among the layered rocks of his homeland, he wrote a line that would haunt geology forever. Earth, he concluded, showed no vestige of a beginning, no prospect of an end. He was describing time so deep it swallowed the imagination whole. Hutton found his proof at a windswept headland on the Scottish coast called Sychar Point. He reached it by boat in the summer of 1788, accompanied by the mathematician John Playfair and the geologist Sir James Hall, and Playfair later wrote that his mind grew giddy by looking so far into the abyss of time. There he saw one set of rock layers, tilted nearly vertical, capped by another set lying flat above them. The lower beds were Silurian greywacke, folded some 425 million years ago. The flat red sandstone above them was laid down roughly 65 million years later. This was an unconformity. The lower rocks had been laid down, buried, hardened, lifted, tilted, and eroded, and only then had the upper rocks formed on top. Each step demanded ages. Stacked together, they demanded an eternity. That eternity found its systematic champion 2 generations later in Charles Lyell. Born in 1797, the year after Hutton finished his great treatise, Lyell abandoned a career in law to write geology. In the 1830s, Lyell built a doctrine called uniformitarianism. He published it across 3 volumes of Principles of Geology between 1830 and 1833, a work that ran to more than 1,000 pages and reached 11 editions in his lifetime. The slow processes we see today, rivers carving, coasts crumbling, sediment settling grain by grain, are the same processes that shaped the past. And if change is slow, then the past must be vast beyond reckoning. Lyell's patient earth did more than unsettle theologians. It handed a gift to a young naturalist who needed time more desperately than anyone. That man was Charles Darwin, and for his theory to breathe, the world had to be almost unimaginably old. In 1859, Darwin published On the Origin of Species, and his entire mechanism depended on time. He had carried Volume 1 of Lyell's Principles aboard the Beagle during his 5-year voyage from 1831 to 1836, reading it as he walked the raised beaches of Chile and the coral reefs of the Pacific. Evolution by natural selection worked through the accumulation of tiny variations, generation after generation, across spans that dwarfed human history. Genesis offered 6,000 years. Darwin needed a canvas millions of times larger. So Darwin did something bold. In his first edition, he tried to measure the past himself, estimating that the erosion of a region of southern England called the Weald had taken around 300 million years. He arrived at the figure by assuming the sea cliffs retreated about an inch per century across a valley some 22 miles wide, then multiplying the slow arithmetic of decay. Only deep time could deliver the slow change biology needed. He planted his flag in the geologists' camp and made himself a target. The attack came not from the pulpit, but from the coldest, hardest science of all. Physics struck back with mathematics that seemed impossible to refute. The man wielding the equations was the most respected scientist of his age. In 1862, William Thomson, soon to be honored as Lord Kelvin, turned his mind to the age of the Earth. Then a 38-year-old professor at the University of Glasgow, he had already laid the theoretical groundwork for the transatlantic telegraph cable and defined the absolute temperature scale that still bears his name. He assumed the planet had begun as a molten ball and had been cooling ever since, its heat escaping by conduction through solid rock. Measure how fast rocks conduct heat. Measure the temperature rising as you descend into mines, and you could calculate backward to the moment the surface first solidified. Kelvin's answer landed like a hammer. His early figure ranged from 20 to 400 million years, and over the following decades he tightened it downward until he insisted on between 20 and 40 million years. To a physicist, the numbers were derived from unbreakable laws of thermodynamics. To a geologist or a biologist, they were a death sentence. Because that number did not merely trim deep time, it crushed it. 20 million years was not enough for Lyell's patient rivers, nor remotely enough for Darwin's slow parade of species. Both geology and biology suddenly found themselves accused of demanding time the universe could not afford. The pressure told on Darwin himself. Stung by Kelvin's authority, he quietly removed his time estimates from later editions of the Origin. In a letter of 1869, he confessed that Kelvin's argument was one of my sorest troubles. And by the 6th edition of 1872, the Weald calculation had vanished entirely. Geologists seethed, resenting the way physics presumed to override their fieldwork with equations they could not answer. But answer they could not. Through the late 1800s, Kelvin's authority dominated the debate, and the Earth grew younger by decree. In this cornered atmosphere, others reached for new ways to time the planet. One of the most ingenious attempts turned not to rock or heat, but to the taste of the sea. In 1899, an Irish scientist named John Joly proposed a beautifully simple clock. A professor at Trinity College Dublin, Joly presented his idea to the Royal Dublin Society, reviving a notion first floated by the astronomer Edmund Halley 2 centuries earlier. Rivers carry dissolved salt into the oceans, and that salt accumulates. If the seas began as fresh water, then measuring how much salt rivers deliver each year and dividing it into the total salt of the oceans should reveal how long the process had been running. Joly's arithmetic produced roughly 90 to 100 million years. It was larger than Kelvin's estimate, yet it too fell far short of the boundless time Hutton and Darwin had glimpsed. The salt clock rested on shaky assumptions, and it could not settle the war. Every method so far had been arguing from the outside. The real revolution would come from inside the atom. It arrived, as revolutions often do, by accident. In 1896, a French physicist named Henri Becquerel left uranium salts resting on a wrapped photographic plate in a drawer. When he developed the plate, he found it fogged, darkened by some invisible emission the uranium had produced on its own, with no sunlight, no external energy. This spontaneous emission was something no one had ever imagined. Matter could pour out energy from within itself, endlessly, for no visible reason. In 1898, Marie and Pierre Curie pursued this strange power, isolating new elements and giving the phenomenon a name that would echo through the century. Working in a leaky shed at the School of Physics in Paris, they processed tons of pitch-blende ore to extract mere fractions of a gram of polonium and radium. They called it radioactivity. At first, radioactivity looked like a curiosity for laboratory physicists, but it carried a secret that would detonate the debate about Earth's age. That hidden energy was heat, and heat was precisely the assumption Kelvin's whole calculation rested upon. The man who lit the fuse was Ernest Rutherford. In 1904, standing before the Royal Institution in London, he announced something that dismantled Kelvin's masterpiece. Radioactive decay, he explained, releases heat continuously inside the Earth. The planet was not simply a cooling ember. It had its own furnace, burning within, replenishing the heat as it leaked away. This shattered the cooling assumption completely. If the Earth generated its own heat, then Kelvin's calculation of how long it took to cool was meaningless. The planet could be vastly older than 40 million years and still be warm inside. And there is a legend, delicious in its irony, that Kelvin himself, then aged 80, sat in that audience and slept through the lecture that undid his life's most famous number. Rutherford did not stop at demolition. He realized the same decaying atoms that heated the Earth could also measure it. If radioactive elements broke down at a fixed pace, then the amount of decay products trapped in a rock would reveal exactly how long that rock had existed. In 1905, he proved it. Uranium decays and produces helium as a byproduct, and Rutherford measured the helium locked inside a mineral to calculate its age. Testing a rock from Glastonbury, he arrived at a figure near 500 million years. It was the first radiometric mineral date in history. The clock had always been ticking. Rutherford simply learned to hear it. Yet helium was slippery, prone to leaking out of minerals over time, which could make rocks seem younger than they truly were. A more reliable decay product was needed. An American chemist found it, and with it he blew every previous estimate to pieces. In 1907, Bertram Boltwood focused on lead. A Yale chemist who had corresponded with Rutherford for years, Boltwood had already shown that lead was the final, stable endpoint of the uranium decay series. Uranium decays through a chain of steps until it becomes a stable form of lead at a fixed, predictable rate. Lead did not leak away like helium. It accumulated faithfully. Measure the ratio of uranium to lead in a mineral, and you could read its true age. Boltwood's results were staggering. Some minerals he tested came back at 2.2 billion years old. He analyzed 43 samples in all, from localities as far apart as Connecticut, Norway, and Ceylon, and his ages ran from 410 million up to that towering maximum. Not thousands, not tens of millions, billions. In one stroke, the timid figures of Ussher, Kelvin, and Joly were rendered laughable. The Earth was old on a scale the human mind could barely hold. But astonishing numbers alone do not make a science. Boltwood's dates needed rigor, careful method, and a defender willing to face down the skeptics who still clung to Kelvin's ghost. That defender was a young Englishman who would spend his life perfecting the atomic clock. In 1913, Arthur Holmes published a slim, revolutionary book titled The Age of the Earth. He was only 23, a recent graduate of Imperial College London, and he had funded his early research partly by prospecting for minerals in Mozambique. He took radiometric dating and made it disciplined, accounting for the decay chains, refining the measurements, and building a rigorous framework where others had offered only tantalizing figures. His earliest reliable estimate placed the Earth at around 1.6 billion years old. Holmes did more than calculate. He fought. He championed the decay clocks against skeptics who could not believe that invisible atoms could out-argue the great Lord Kelvin. Year after year, Holmes pushed the accepted age upward, past 1 billion years and beyond, dragging science toward the truth one measurement at a time. By 1927, he had revised his estimate to between 1.6 and 3 billion years, and in 1946, he offered a figure of roughly 3.35 billion, edging ever closer to the answer. But even Holmes could not yet name the final figure. One piece was still missing. The problem was that Earth's own rocks are restless. They melt, reform, and are ground down and reborn, erasing the record of the planet's true beginning. To find the moment of creation itself, someone would have to look beyond the Earth, to stones that had never changed since the solar system was born. That someone was Claire Patterson. In 1956, he turned to meteorites, the ancient debris left over from the formation of the planets. He studied lead isotopes locked inside fragments of the Canyon Diablo meteorite, the iron mass that had blasted a crater into the Arizona desert. These metals held the pristine chemistry of the solar system's dawn, Patterson's measurement was the one that finally held. He calculated the age of the Earth at 4.55 billion years, with an uncertainty of only 70 million years either way. After 3 centuries of argument, between scripture and rock, physics and biology, guesswork and genius, the planet had at last been given its true age, and that number has barely moved since. Today, the accepted figure stands at 4.54 billion years, and it does not rest on a single measurement. It has been confirmed again and again by multiple independent isotope systems, different elements decaying at different rates, all converging on the same answer. When many separate clocks agree, doubt runs out of room. The oldest fragments of the Earth we have ever touched are tiny crystals called zircons, found in the Jack Hills of Western Australia, dated to 4.4 billion years. They are older than the oldest whole rocks, survivors from the planet's fiery infancy, carrying their birth date locked in their atomic structure. They are proof that the clock was running from the very beginning. And so the long war ended not with a sermon, not with a cooling curve, not with the taste of salt in the sea, but with the patient, unstoppable decay of atoms hidden inside ordinary stone. Atoms became earch's truest helost cloque. From Ussher's 6,000 years to Patterson's 4.5 billion, the story of Earth's age is the story of humanity learning to read a timepiece it did not know it held. Every rock beneath your feet is quietly counting, and now, at last, we know how to listen. If this journey through deep time moved you, consider subscribing to follow more stories of how we came to know our world.